In number 11 on the chapter 1 test, you have to give an equation of a function having all these different characteristics. So a removable discontinuity at x equals 2, remember that's when stuff cancels. So if I just put an x minus 2 on top and an x minus 2 on the bottom, well, that'll be, I know that that looks just like the line y equals 1, except for the fact that there's a hole at 2. So that works for the first part. Done. Vertical asymptote at x equals 6, I get those asymptotes when stuff in the denominator doesn't cancel. So if I throw in an x minus 6 down here, well, now that's done too. And if I need a horizontal asymptote at y equals negative 1, right now, my horizontal asymptote, if I look at the end behavior model, I've got this, x over x squared, which is 1 over x. Well, as x goes to infinity, this goes to 0, y goes to 0. And as x goes to negative infinity, same deal. So I'm just going to put plus minus infinity, y goes to 0. Well, I want it to go to negative 1. So what I could do is just subtract 1 from everything. Right? If I just subtract 1 from everything, that just moves the entire graph down 1 unit. So that works. What some other people did was instead they changed their end behavior models. So this is one example that works. Another example that works that I saw and I thought was pretty clever was this one. If you multiply this by negative x, right, then your end behavior model is going to be negative x squared on top over x squared on the bottom. Well, that turns into negative 1. So regardless of what x is out at infinity or negative infinity, however big it is, you always going to approach negative 1. So this one also works. The one example that you can't do, well, a lot of people did negative x plus 1, negative x plus 2, negative x plus 3. The one example you can't do, unfortunately, is negative x plus 6. Because negative x plus 6, if you do that, this right here is really the same thing as negative 1 x minus 6. And so that's going to cancel here. These are going to cancel, leaving you with negative 1 there. So yeah, it will approach negative 1, but now you actually have created a removable discontinuity at 6 instead of a vertical asymptote at 6. So this one doesn't work, unfortunately. In number 12, 12 is a parametric one. And I made it a more applicable parametric instead of just random parametric equations. So the first question is, at what time is the ball 30 meters above the ground? Okay, well, x is how far along the ground distance it is, and y is how high up it is. It says, where is it here? Y is the vertical displacement, so it's the height. X is how far it is from you. So when is the ball 30 meters above? Well, that's the y. That's when y is 30. That's what you're trying to answer. So we know that y is 40t minus 4.9t squared. Most people wrote down this equation and then weren't sure how to solve it. I think the easiest way to solve it is to graph this as y1 and this is y2 and see where they intersect. You could also use quadratic formula. Either way, if you solve it, you should get two t values, right? Because if you think about it, it's going to hit twice, right? It's going to hit at some point here and at some point here. Now, the x-axis here isn't time. So this doesn't say, oh, it's going to hit at this time and at that time. That tells you how far along the ground it's going to be at a height of 30. So if you want to figure out the times that it's 30, you're going to need to actually solve this equation right here. So if you solve that equation using quadratic formula or using the intersections on your calculator, you'll get two t values. One of them is about 0.8355 seconds, and the other one is about 7.3277 seconds. Those are our two t values. Then you need to find x for these times. Well, x is 20t. X equals 20t. So really all you got to do here is multiply each one by 20 times 20. And that's going to give you x is about 16.71 meters. And then if I multiply this one by 20, right, then I'm going to get x is about 146.555 meters. We'll do approximately. So there are my two x's that go with my 2 times. All right. In the next one, it says a fence 2 meters high is at x equals 160 meters. So according to this, to the parametric function I gave you, will the ball go over the fence, or hit the ground? And then you got to justify your answers. So the fence is 2 meters high when x is 160. Well, I know from my equation that x is also 20t. So that means when x is at 160 meters, that's when the ball has been in the air for 8 seconds, because that's what t is going to be. So if I can figure out the height of the ball when t is 8, then I can figure out if it goes over the fence, under the fence, or hits the fence. So let's plug in 8 into y, right? Because y equals 40t minus 4.9t squared. So if I plug in 8, I got 40 times 8 minus 4.9 times 8 squared. And if you plug that in, you're going to get 6.4 meters. Well, 6.4 is a lot higher up than 2. So when t equals 8, the ball is right above the fence. It's 4.4 meters above the fence. 6.4 meters is a lot higher up than 2 meters, and so it will pass over the fence. And it passes over the fence when t equals 8 seconds. Okay, so then the last part is get rid of the parameter t, right? So to get rid of the parameter t, let me rewrite these equations. X equals 20t, y equals 40t minus 4.9t squared. So if I want to get rid of the equations, if I want to get rid of the t, the easiest t to isolate is right here, right? X over 20 equals t. Well, now take that and plug it in here and there, right? So y is going to be 40 times x over 20 minus 4.9 times x over 20 squared. So then that's going to become 2x minus 4.9 over 400, 20 squared, times x squared. And then it says give your answer in this form, so if you just rearrange it a little bit, I wasn't picky about that. As long as you had something close to it, then that was good enough for me. So there it is. Okay, hope that helps. If you're still unclear about how anything on this test works, come find me early in the week so we can go over it together.